Okay, in about an hour I'm going to post the next homework assignment onto Blackboard, homework 6, and it's covering a range of topics as far back as estimating wastewater quantities, including a problem related to like the flow capacity in a partly full sewer pipe. There's going to be a problem in there related to settling, which we'll talk about today. So it's kind of a catch-all assignment that'll take us up through chapter 21, which is what we're talking about today. So you've got a week to work on that assignment. And just a reminder about the homecoming barbecue tomorrow. Even if you haven't RSVP'd yet, you might as well show up. I think we're going to have plenty of food. So, it's looking like the weather's going to be nice. The food's going to be delivered at noon. And there's going to be people playing cornhole and other lawn games, and so we'd love to have you there. Also, the Army Corps of Engineers is hosting the Employer Spotlight Series lunch on November 9th. And the way that those work is at 11 o'clock they have a buffet lunch over at the upstairs second floor dining room. And then at 12 they have a presentation. And so if you want to attend that, you'd need to skip our class meeting, but I'd consider that an excused absence if you'd like to do it. So just let me know. Actually, what you need to do to register is contact Tanner Drown. So he's the co-op coordinator for the college. All right, so any questions related to the announcements? All right, we're talking about primary treatment today. And there we go. Just to set the stage for where things are at, this is a schematic of a wastewater treatment plant, and you can kind of guess what this is because we've talked about bar racks already and screening. And so here stage 1 would be kind of a catch-all for any kind of conditioning that's being done to remove grit, remove debris. It could include a comminutor, which is grinding up any particles that need to be, have their size reduced. What we're talking about today is primarily the first clarifier that exists in wastewater treatment. The clarifier generates primary sludge. And the primary treatment objective here is to try and remove anything that will settle to the bottom or anything that will float to the top that's not dissolved into the water. And so BOD, this pollutant that we're eager to remove from wastewater because it suppresses the oxygen concentration in the water that's going to accept this wastewater, BOD exists both as particles and it's dissolved in the water. And so through primary treatment, we're trying to remove as much as of the particulate BOD as we possibly can. And so suspended solids is just referring to that solid fraction of the waste that has to be removed. And some of it is organic and some of it is inorganic. So there's both colloids, which are inorganic minerals like clay particles in wastewater, but then there's also suspended organic material, and we can remove a little bit of both through primary treatment. Here in green is secondary treatment, which we'll talk about in a bit, and some people have described secondary treatment as one of the greatest inventions of the 20th century, that there are few ideas that have had a more positive impact on the environment than secondary treatment. So I mean, that's a pretty high bar, that saying it's one of the best engineering achievements. So we'll talk about why they make that claim. For a lot of years, primary treatment was all that wastewater treatment plants did. They would settle out grit, they'd remove debris, they'd do a little bit of taking the scum and grease off the top, settle any sludge that they could, and then the supernatant from the primary clarifier, which is that which flows off the top, would just go straight into rivers. So that was about until the 1950s that it became more common for primary treatment to be just one component rather than the main component. So let's look at a brief video that talks about primary treatment. No commercial for this one, which is a treat. All right, let me stop the recording. So, sounds like a lot of trouble just to preserve some fish, right? I mean, it's actually more than that. I mean, he says that, the purpose of having the BOD consumed at the treatment plant rather than the stream is to prevent the dissolved oxygen from sagging too low in the stream so that you preserve fish. But the other issue is that it's for our benefit as well, not just the fish, because if the stream becomes anaerobic, then it's going to smell really bad. The waste would continue to be degraded in the absence of oxygen. Then any sulfur that was in the waste would form into hydrogen sulfide or related compounds that on the one hand can be toxic and odorless in the case of hydrogen sulfide, but there are also other compounds which, when degraded anaerobically, have really terrible smell. So if you don't smell it, it's dangerous because you don't know that you're exposed to hydrogen sulfide, which is this toxic compound. But then the flip side of it is that the smell can really be bad. So it's in part to preserve the aquatic species, but also to preserve our sanity and ability to coexist in the vicinity of, that's a little too dark, in the vicinity of the stream that's receiving wastewater. Let's see, they had this side view, right. So it just kind of makes the point that both along the bottom is some sort of a rotating squeegee-like device, and then also at the top is something which is removing the scum. And so the quiescent conditions inside of a settling basin are really important to allow that to be accomplished. So we've talked about this before in the water treatment aspect of settling, where mainly our focus was on type 1 settling. Type 1 settling we addressed through the Stokes equation, which assumed that we had spherical particles which settled downward in the absence of any interference with other particles. That a particle settles without any further collisions as it's traveling downward and contacting the bottom of the clarifier. The difference between that, which we were talking about in water treatment, and wastewater treatment is that in wastewater treatment it's more common for the concentration of solids to be much higher. And so we're not going to have that type 1 settling. We'll have type 2 settling, which is flocculant settling. But in both cases, the important design considerations are that we need to have baffles that distributes the incoming water across a large cross-section to reduce the velocity, because we don't want any kind of jets or eddies inside of the settling zone that would suspend or interfere with the particles as they're settling downward. We want to have really slow-moving flow in the settling zone. And then the other way that we make that happen is by distributing the outflow over a large cross-sectional area. Because remember that the continuity equation, which says the flow rate Q is the velocity times the area, if you want to have a low velocity as the water exits the settling zone, then you need to have a large cross-sectional area. So small v, large A to get the flow rate that's needed. And so the way that we maximize area is with those V-notched weirs in the launder. So evenly distribute the incoming flow, calm quiescent settling conditions, gradual movement of any kind of device in the sludge zone that won't send, number one, the sludge back upward. We don't want to disturb the sludge that's settled, but then at the same time you don't want to have any kind of vortices coming up into the settling zone from the sludge wiping mechanism. There are the same kind of hydraulic loading rate parameters used for primary clarifiers in wastewater as were applied in clarifiers for drinking water. The overflow rate, sometimes called the loading rate, is the flow rate of the water divided by the area, the top view area of the settling basin. So basically the area over which the particles are settling down to rest on. In the case of rectangular basins, there may be a cumulative length of between 15 to 100 meters depending on the flow rate. Typically they're longer than they are wide because we want the water to be flowing in a plug flow manner, and we've talked about how that can be accomplished. To really ensure plug flow, you'd have baffles between segments, and depths of between 2 to 5 meters are typical, partly because any deeper than that and you're having to lift the water up at a higher distance with some sort of a pump, but then also just the pressures become higher and leaks would be more common. So here's the formula for the loading rate that we can use to assess how much water is getting into a horizontal clarifier. It's the flow rate that's being treated and then the cross-sectional top view of the clarifier. Circular clarifiers are also common. In addition to rectangular clarifiers, the water is moving up towards an outward weir that goes along the edge of it rather than just being at the end of a rectangular clarifier, and so the water is moving radially in the case of a primary clarifier that's circular. Both of them will have some sort of a mechanism to scrape the sludge towards a central area where the sludge is pumped away. So just to get some additional practice with the numerical side of primary clarifiers, let's say that we have a flow rate of 1.2 cubic meters per second, and we're going to use circular clarifiers in this case. A pair of clarifiers because we need there to be some redundancy so that we could maintain and inspect the clarifier. We wouldn't want to have just a single of them. So we've got two of them, and each are 35 meters in diameter. So first we need to calculate what's the effective overflow rate, and the suggested guidelines say that overflow rates are typically between 25 and 60 cubic meters per day per square meter. So let's see in this case if we load 1.2 cubic meters per second into these two 35-meter diameter clarifiers. Are we within that range? And then you can see in part B we want to calculate the hydraulic detention time. And so part A, first of all we need to calculate the area, and the area is going to be pi d squared divided by 4. And then the next thing we want to do is calculate the loading rate, which is the flow rate divided by the area. Okay. Now in part B, the hydraulic detention time, we're going to need to calculate the volume of these clarifiers, and they're cylindrical. So we've got a circular cross-section and some certain distance of a depth that's defined. So we're going to have some area that we've calculated in part A, and then a depth of 3.2 meters. Okay, so then the volume is area times depth. And the time is going to be the volume divided by the flow rate. And that'll tell us the hydraulic detention time. And then part C is just trying to figure out how much mass of BOD would we be removing if we know it's 250 milligrams per liter. So let me pause for a second, give you some time to begin on part A and B, and we'll check in on the answers to that before we move on to the BOD part. So for purposes of this example, we are assuming that the clarifiers are operating in parallel, meaning that the flow is split half and half to each of the clarifiers. So one of the clarifiers will get 0.6 cubic meters per second. The other one would also get 0.6 cubic meters per second. Now, if one of them was out of operation, then that would be totally changed. But let's just look at it when both of them are functioning. So I've got the calculations I did up on the screen, and so what you can see is if we have a total of 1.2 cubic meters per second, then each one of the clarifiers should get 51,840 cubic meters per day. And then we find the area of one of the clarifiers, and so then the loading rate that's going is 53.88 meters per day. And this units of meters per day is the same as cubic meters per day per square meter. So they sometimes call it a loading velocity because it has units of length per time. You'd get the same number if you had kept the 1.2 as the flow rate and then you just found the total area. So if you found the total area and used the full flow rate, you'd end up with the same 53.88. And it's at the high end of the loading rate, but the normal range goes between 25 and 60, and so, you know, this is in the ballpark for sure of what a clarifier should be able to handle. So now, calculating the volume in one of these clarifiers, we're going to have to multiply the area that we determined by the depth. So let me show you that here. You know, just sometimes for visual inspection you can get a sense of the scale of things. You know, the rate that water's coming into a tank, the relative size of the tank. If this had said that it was going to be in the tank for 55 days, then, you know, maybe we'd scratch our heads and wonder if we'd made a calculation error along the way. Or if it said it was going to be in the tank for 55 seconds, you know, that's visually not obviously true. When we looked at the video, for example, of a clarifier, how slowly the water's entering, how little goes out in each time increment. Now, what about this question of the BOD? So 250 milligrams per liter, and we want to know how many kilograms per day is removed by the system. So it's removing 35% of 250 milligrams per liter. Okay, so for part C, what we're saying is 0.35 of 250 milligrams per liter. Now let's put that into units that are more useful for us. It is 0.25 grams per cubic meter. We've got how many cubic meters per day from the entire system. That's not just one of the clarifiers. So we had found that the Q total was 103,680 cubic meters per day. That's the overall flow rate. $250 milligrams per liter. Oh, no, that's a mistake. So it'd be 0.25 grams per liter, or 250 grams per cubic meter. Is that right, Josie? Yeah. Sounds like you were going to catch that as well. 250 grams per cubic meter. That's more like it. Okay. So that means with 35% efficiency, we're actually removing out 87.5 grams per cubic meter. So we multiply the amount of removal by the flow rate. And so we're removing 9,072 kilograms of BOD per day. So if we had dumped this wastewater directly into a stream, it would need 9,000 kilograms of oxygen per day to break down the waste. So what we're going to do instead is break down that sludge. The stuff on the bottom that we're sucking out, that's going to be broken down. It could happen either anaerobically in some sort of a sludge digester, or the sludge can be thickened and dewatered and then applied over the land, and the BOD could be broken down that way. Any questions on this example? Okay. Well, let's talk a little bit in more detail about the type 2 settling that's happening. Type 1 settling was an individual particle assuming that it's spherical and that there's no interference as it goes down. Type 2 says that the particles are going to interact with one another. And our book describes that as orthokinetic flocculation, where particles are colliding and the flocks are growing as they interact with each other. And it's partly because of fluid motion that brings the particles in contact, but it's also differential settling velocities that brings these particles in contact. There is an equation that's introduced in our book that describes the rate of the rate that the number of particles decreases in the tank. And when we have a pair of particles coming together, some fraction of those collisions is going to result in a successful joining of the two flock particles. And so not every collision is going to cause like two particles to become one. And that's accounted for here in this term for collision efficiency. You can see that the formula takes into account the velocity gradient, and you probably remember back to earlier in the course that we talked about mixing energy in flocculation basins. And so here it's not necessarily that we're artificially agitating the water, but the velocity gradient is maybe just related to Brownian motion, or the gravity of the particles downward can be moving the particles relative to the stationary fluid around it. So there's some way that we describe the mixing energy that is in the settling basin as the particles are settling, some parameter that predicts what fraction of the collisions join particles together. And then you can see that the initial number of particles is another parameter that describes the rate of change of how quickly is the number of particles going down in a basin because of these collisions. If we integrate, then we can get in a formula that says what the number of particles per unit volume is relative to an initial number of particles per unit volume. And we estimate the number of the volume that's occupied by a certain unit volume of water. So this term is saying if you've got, for example, a cubic centimeter of water, what fraction of that volume is occupied by particles relative to what fraction of it is occupied just by the liquid itself. And this assumes uniform particle distribution. You have to know the diameter of the particles, and it assumes that they're spherical, but at least we're not assuming that the particles are settling without any interaction between them. Now, this actually, this model works pretty well, except for that there are a couple of deviations from this theoretical behavior. And one is that this would predict this idea of orthokinetic flocculation would say that if you gave the particles an infinite amount of time, that eventually you just end up with one particle, because they, statistically speaking, the last two particles would bump into each other, and then there'd just be one massive particle that had settled to the bottom of the tank. But the reality is that at a certain point, the flock is being destroyed at the same rate that it's growing because of the wiping mechanism at the bottom is adding a little bit too much mixing energy, and so a really large flock particle would be too delicate. And so as the particles get larger and larger, they become progressively more delicate, and so we get up against this limit of how large the particles can be for whatever velocity gradient is there. And you remember that when we were talking about flocculation in drinking water treatment, we had decreasing G values in successive flocculation basins. Maybe we started with a G value of 85 inverse seconds, then down to 50, and finally 20 in the last mixing chamber. But in a single clarifier, the mixing energy is just about how much velocity is in the water because of the particles settling themselves and vacuuming out the sludge from the bottom. So we can't really control, you can't go down to zero velocity gradient. So this first bullet point is just saying that there is a limit of removal efficiency, in part because as the particles get larger, they're more likely to break. But then the other aspect of it is if we leave particles too long in the clarifier, then they start to consume all of the oxygen that's in the water. And when they've consumed all of the oxygen that's in the clarifier, then they will begin to degrade anaerobically. And that can have the formation of gas bubbles, which will begin to, when they're formed at the bottom of the clarifier, they begin to rise upward, and then they'll suspend the particles that are trying to settle down. Those little gas bubbles, as they go up, will cause the flocculating particles to float rather than to settle. So that's why we don't try to have the settling basin operate for 12 or 18 or 24 hours, is because the performance just wouldn't keep improving. There's kind of a threshold limit. Okay, so let's get some practice using these equations for the following case, where we assume that we have these 5-micron particles that are going to be settling downward. So they're really small particles that will, as they settle downward, combine together and form larger particles through flocculant settling. So, by the way, 5 microns, this diameter of 5 nanometers is 5 times 10 to the minus 4th centimeters. And the reason why I've specified that in centimeters is that our number of particles per unit volume, 10,000 per milliliter, that's the same thing as saying that we have 10,000 particles per cubic centimeter. So we'll calculate in the volume in units of cubic centimeters just because of the way that things are going to be substituted together in this first calculation. Okay, so we have our velocity gradient is 185 inverse seconds, and the collision efficiency is 90%. So here we're saying we don't assume that every collision yields in a larger particle, but 90% of them do. 0.90. Okay. So pi d cubed n divided by 6, and we're going to use the initial number of particles per unit volume here. So calculate the calculate with the diameter that's given of 5 microns, and then try and determine how much time it's going to take to have half as many particles that we started from. So we had this initial number of particles was 10,000, and that's what we use here. But we want to ultimately know how long does it take to get down to 5,000 per cubic centimeter through flocculant settling. Let me pause for a second and give you a chance to calculate these. So 6.55 times 10 to the minus 7th. It's unitless because that's saying if you have a certain volume of water, what fraction of that volume is occupied by the particles. And it's going to be so small because these particles have a diameter of 5 microns, and there's only 10,000 of them in each milliliter. So that's why this is such a spectacularly small number, is that there's hardly any volume occupied by these particles. The volume is mostly water. You know, it's 99.999% water, really mostly water. But we calculate omega, and from that we're going to be able to determine the amount of time it takes to have those particles cut in half. Because, you know, here's the version of the formula that we're going to solve, but we want to solve for t, which is in the exponent of this e function. So we need to take the logarithm of both sides to get that down out of the exponent. So the logarithm of the ratio of the final number of particles to the initial number of particles is equal to minus 4 times n divided by pi times g omega times t. So we're solving for the time that it's going to take to go from 10,000 particles to 5,000 particles. So just rearranging that algebraically to solve for t. Let me pause for a second and give you a chance to substitute in the numbers there. So the two good things that happen during this time that we're calculating is the number of particles is decreasing because of collisions, but then also the location of the particles in the settling tank is getting lower and closer to where they can be swept out as sludge, and further away from the effluent location where the clear water is going out of the top. So when we substitute in the values here, it tells us it should be about 1.39 hours. 1.39 hours in this case. Now, this is a little bit simplified though, because omega was a function of the number of particles, right? And with each passing minute, there are fewer particles. So I think to do a more accurate calculation of this, what we'd need to do is we'd need to find out, for example, how long does it take to go from 10,000 to 9,000 particles? Break it up into smaller steps. And then how long does it take to go from 9,000 to 8,000 particles? Because in each case, omega would be a little bit different, because omega itself depends on the number of particles. Here we've just assumed it's the number of particles at the beginning of a time increment, but this gives us a rough idea anyway. Any questions about type 2 settling? All right, so we'll leave it there for today. Remember that what's on your radar is come eat barbecue with us tomorrow. Think about going to the Employer Spotlight series. And then this afternoon I'll be posting homework 6 on Blackboard. So I'd encourage you to get a start on that over the weekend.